Welcome back, guys. Welcome back to our second video of Stats Masterclass. And in this video, we are going to cover the engine of the car. We're going to open the hood of the car. These two topics are very important because, as I said, they are the engine. If you understand these, you can drive. If you don't, trust me, you'll crash. Today, we are going to cover firstly the zoo of animals, the zoo of distributions, and the magic trick, which is the central limit theorem. These are the two topics that we're going to cover. So, firstly, on your screen, again, is our PrepNip statistics interview Bible. The link for this, for the drive where you can find this Bible, is in the description and the first comment, as well as the link to our WhatsApp group. So, do check them out. Getting straight to our content here. First thing that you see is Bernoulli and binomial, right? Bernoulli. This is the atom of statistics. It is a single trial with only two outcomes. A success is a 1 and a failure is a 0. So it has only two outcomes. For example, a single coin flip or a single customer clicking buy, right? It is controlled by only one thing, probability. If p equal to 0.5, it's a fair coin. If p equal to 0.1, let's say customer click. So if p equal to 0.1, then it's hard to sell, or the probability of the customer clicking is low. So it is only controlled by one thing, p. That is why the p part, this is a success probability. Okay. So this is the first concept, very basic concept. As you can see, Bernoulli, and in the bracket you can see p, because it is controlled by only p. Yes or no. Single trial with only two outcomes. Next is your binomial. Binomial, this is just a bag of Bernoulli trials. It models the number of successes in n independent trials. That is why an extra parameter n is added, because it models the number of successes in n independent trials. Example, this time you don't just have one customer, you have 100 visitors or 100 customers to your website. How many clicked the button buy? That count as binomial. Okay, you have n comma p. It's just a bag of Bernoulli. Why? Because it counts or models the number of successes in n independent trials. You can have a look at the graph here. It's a hump, right? You can see it's a hump kind of a thing. You usually get the average number of clicks, and getting 0 or perfect score is rare. Usually you get the average number of clicks. That is why it's a hump. And we'll discuss about this hump in detail as well. Okay. So when does binomial fail? The binomial actually fails. It's written here in front of you that binomial assumes independence and constant p. What I'm saying is that binomial assumes that, for example, if 100 customers are visiting your store, all of them are independent. But let's say they talk to each other before coming to the store. So then there's going to be a bias, right? I talk to my friend and my friend says that store is bad. Then my chances of buying something are less, right? Or that website isn't good. Then my chances of buying something are less, right? So this is the trap for binomial. This is the interview trap. That if the customers talk to each other, or if the independence isn't there, the binomial fails. So remember this part, that binomial assumes independence and constant p, but in reality, if it's not the case, then binomial fails. Then let's jump on to Poisson. Counts events in time/space. Okay. This technically counts how many times something happened in a fixed interval. For example, 1 hour or 1 mile. This is the interval, by the way. Imagine you are a 911 operator, or let's say someone who's sitting in a call center, right? You sit there for an hour. How many calls do you get, or how many calls do you make in an hour, right? Or how many kilometers do you run in an hour? So it usually counts how many times something happens in a fixed interval. It could be 0, it could be 50. It again usually hovers around the average. This also usually hovers around the average, called lambda. Okay. Look at the text here. Mean equal to lambda, variance equal to lambda. This is the fingerprint of Poisson. Literally, this is the fingerprint of Poisson. Why? It means as the rate gets higher, the spread gets wider naturally. The spread naturally gets wider as the rate gets higher. Okay. Now the trap in Poisson is that if your data is clumsy, okay, and all these traps are very, very important because in interviews they want to make sure कि आप trap में ही फंसो. So the thing is with Poisson, if your data is clumsy, the variance will be huge, right? For clumsy data, variance is huge. And variance will be much bigger than the mean. In Poisson, what we say? Mean equal to variance equal to lambda. But for a clumsy data, variance will be greater than mean. And if variance is greater than mean, that is when your Poisson fails because this condition fails. So this is something that you have to keep in account in your Poisson वाली मतलब Poisson test कि clumsy data पे Poisson fail हो जाता है. ठीक है. Now let's move on to counting failures before we succeed. Geometric. How many trials until the first success? Geometric का मतलब ये होता है. ये जो geometric P है ना, this is basically how many trials before the first success. Let's say you're a salesman. You knock, get rejected. You knock, you get rejected. You knock, you get rejected. How many knocks or how many door-to-door visits did it take for you to make your first sale? That is what geometric means. Look at the shape here. It starts high and drops fast, right? Why? Because it's most likely you succeed early. It's rare, right? It's rare to fail 100 times in a row. I hope you get it what I'm saying. कि 100 बार लगातार fail होना is a rarity. That is why early it starts at a high and बहुत ही तेजी से it drops. Why? Because the probability of you succeeding early is ज़्यादा as compared to बाद में. And it's a rare thing कि तुम 100-200 बार लगातार fail हो जाओगे, right? So that is why this is the shape of the graph. So the geometric concept is how many trials until the first success. Negative binomial. Negative binomial R comma P. These are the two parameters. R comma P. Negative binomial is about, let's say, पिछले में geometric में we discussed about a salesman, right? In this, let's discuss about a stubborn salesman. It models trials until the rth success. उसमें क्या था? How many geometric में था? How many trials until the first success? Negative binomial में है it models trials until the rth success. For example, let's say your boss says you're the same salesman and your boss says you can't come home until you make 5 sales. Now, how many doors do you knock on? How many doors do you knock on before you make 5 sales? Not your first success, 5 sales. So this is the only difference between geometric and Poisson, that it models trials till the rth success. Okay. Negative binomial is good when variance exceeds mean. Remember this. It is more flexible for over dispersed counts. If your data is too messy for Poisson, use your negative binomial. This is a pro tip, that if your data is messy, clumsy, right, your Poisson is going to fail, because then variance will be greater than mean. Poisson में we cannot afford. याद करो, अभी अभी पढ़ा था. तो अगर क्लमजी डेटा है, पॉइजन फेल हो रहा है, नेगेटिव बाइनोमियल यूज कर लो, काम बन जाएगा. ठीक. दिस इज अ प्रो टिप बाय द वे. ओके. नाउ लेट्स लुक एट यूनिफॉर्म डिस्ट्रीब्यूशन. यूनिफॉर्म ए कॉमा बी, ये जो सामने लिखा है आपके. Every value in a range is equally likely. This is what uniform का concept is all about. Every value in a range is equally likely. For example, a perfect spinner board, or waiting for a bus when you have no idea when it comes. Every value in a range is equally likely for you. That is what uniform means. ठीक है, कि मान लो एक ऐसी स्ट्रिप बनी, तो ये इसकी भी उतनी ही लाइकलीनेस है, इसकी भी, इसकी भी, इसकी भी, इसकी भी, इसकी भी, सबकी इक्वल लाइकलीनेस है. इट मॉडल्स इग्नोरेंस. व्हेन यू डोंट नो एनीथिंग, यू अज्यूम यूनिफॉर्म. जब तुम्हें कुछ भी नहीं पता तो तुम यूनिफॉर्म मान लेते हो कि सब चीजों की प्रोबेबिलिटी इक्वली लाइकली है. द every value in a range is equally likely because मुझे कुछ भी नहीं पता. Then comes your exponential. Exponential ब्रैकेट में लैम्डा लिखा है. This models the waiting time between events. This models the waiting time between events. Because नहीं, in this case, not every value is in a range is not equally likely. Remember, we took an example of, let's say you are, let's say 911 operator हो आप. So Poisson में, if you remember, 911 operator वाली चीज हमने बात की थी. Now exponential will model the time between call 1 and call 2. Time between call 1 and call 2 is exponential because it models the waiting time between events. The magic part is it is memoryless. By memoryless, what I mean is, if you have waited 10 minutes for a call, the probability of it ringing in the next minute is the same as if you just sat down. The universe doesn't owe you a call. It is memoryless. अगर तुम 10 मिनट से भी वेट कर रहे हो, तो भी the probability of the call ringing the very next minute is the same as if तुम 10 मिनट से वेट नहीं कर रहे थे, you just sat down. That is what I want to say. So it's a memoryless thing. This is the magic part also. Remember this. Peak. I hope exponential is clear now, what it models. Then comes your normal distribution. Mu, comma, sigma square, n. Right? The bell curve. It is symmetric and defined by mean and variance. Bell curve is symmetric and defined by mean and variance. Why is it normal though? Why do we call it normal? This is the bell curve, by the way. Ghanta. This. But why is it normal? Because it happens when you add up huge amounts of tiny independent things. Remember, इसको मेरे साथ अपने मन में बोलो. It is normal because it happens when you add up huge amounts of tiny independent things. Height is normal because it's the sum of, okay, your height. Example दे रहा हूँ कि your height is normal because it's the sum of genetics plus diet plus environment plus sleep plus exercises, whatever you did. Sum of a lot of things. You add up huge amounts of tiny independent things to make something normal, right? That is why it is known as normal. Normal distribution का concept ही यही है. It is normal because of this. Again, repeating, very important. It is normal because it happens when you add up large amounts of tiny independent things. The rule is, and memorize it. 68% of the data is within one standard deviation. This is the mean. Let's say one standard deviation is this. So 68% of the data is within one standard deviation. इतने में 95% is within two standard deviations, and 99.7% is within three standard deviations. We convert messy data to z-score. By the way, this is z, x minus mu upon sigma. X is the value, again mu is the mean, sigma is your standard deviation. So this is how you convert. And we convert messy data to z-scores to see how many sigmas we are away we are, by the way. How many sigmas or how many standard deviations away we are, we convert it into z-scores. By the way, I'll create a separate 7-8 minute video on normal distribution separately because it's a very important concept. So I think I'll upload it tomorrow. Now, students' t distribution. It's normal का cousin ही है, but normal का थोड़ा careful वाला cousin है. It looks like a normal curve but shorter and fatter. हल्का छोटा सा हल्का गोल सा है, मतलब ये मान लो थोड़ा careful cousin. Normal curve but a bit shorter and fatter. We use this when our sample size is small and we don't know the true spread. That is, we don't know the standard deviation of your population. तुम्हें नहीं पता. And your sample size is small, in general less than 30. And you don't know the sigma of the entire population. You don't know the true spread. That is when you use your t distribution. Look at the graph on page in front of you. Now, the orange line that you see, right, is higher in the tails, but the blue line that you see, this, okay, the orange line that you see is higher in the tails than the blue line. That represents extra uncertainty. Extra uncertainty क्यों? Because you need to make sure that you are not overconfident when you have little data. तो ये जो आपका t distribution है, आप देख रहे होगे कि tails पे it is higher than your blue line. Blue is your normal. So the thing is कि यहाँ पे you are taking into account the fact that your data is small. The sample size is small. So if your sample size is small, you take into account this particular thing and extra uncertainty को account में रख के overconfident होने से बचते हो. So remember this part. This is also a pro thing. T versus normal distribution में ये चीज होती है कि T distribution की tails are higher than the normal distribution. Only because of this, कि sample size smaller, so we don't want to be overconfident. So we take into account extra uncertainty. Okay. Now your chi-square distribution, F distribution, log normal. I think I'll skip this again because I don't think interview perspective से ये इतना important है कि आप इस चीज पे ज्यादा ध्यान चलाओ. And I think we should straight away jump on to sampling in CLT because इतना भी अगर आपको zoo of distributions के बारे में पता है जितना मैंने बता दिया, then I think you're good enough for your interviews. बाकी अगर आपको बहुत ज्यादा डिटेल में है तो we'll create a separate detailed video for chi-square and F and let's say beta, gamma और इन सारे distributions के V-bull distributions and all of them, इनके बारे में we'll create a separate video. बट इन दिस वन आई थिंक आई वांट टू कवर अगेन 2 सिग्मा तक का 95% तक का स्पेक्ट्रम, कि 95% लोगों के इंटरव्यू में इससे आगे नहीं पूछा जाता. तो now let's jump on to sampling and the CLT and why averages behave better, right? So अब हम zoo से बाहर निकलते हैं. Sampling distribution versus data distribution. Real data is actually ugly and skewed. It's not a bell curve. So bell curve nahi hai, तो you think you can't use easy maths, right? The solution to that is central limit theorem. Solution to your clumsy and skewed and ugly data पे maths लगाना is your central limit theorem. The magic is that you have a messy bucket of data, which is the population. You scoop out a cup of data, which is the sample, and find the average. And you do that a million times. The averages of those cups will form a perfect normal distribution, even if the original bucket is messy. समझ आया? The thing is, you have data, log normal data, let's say in real world, which is very clumsy, very ugly and skewed, and it's not a bell curve. तो तुम normal maths नहीं लगा पाओगे, right? Now, the thing is, इसका solution central limit theorem होता है. What central limit theorem says is, you have a lot of data. ठीक है, messy bucket of data है तुम्हारे पास, which is the population. Now, उसमें से एक छोटा सा स्कूप बाहर निकाल लो. कल if you remember the pot of soup, उसमें से एक कप 500 कप सूप है, एक सूप बाहर निकाल लो एक कप का. This is your sample. Now find the average of this sample. Now take million samples from your data and find the averages of all those million samples. Now when you plot the averages of all those cups, all those samples, the averages will form a normal distribution. So this gives you a license to operate कि आपकी original bucket messy थी, पर आपने million times sampling करके, मतलब बहुत बार sampling करके हर एक sample का average निकाल के plot कर दिया. Now that average का plot is the normal distribution. So this is the license to operate. It allows you to use normal maths on messy, clumsy business data. This is what your central limit theorem is. Nothing else. Standard error. Uncertainty of an estimate that's written in front of you. People at times mix up standard error with standard deviation. It's not. Standard deviation measures the spread of the data. How different are the customers? Standard deviation measures the spread of the data. Let's say how different are the customers. Standard error measures the spread of the average. How precise is my estimate? You can see it's written sigma upon root n, SE, or S upon root n, which is S means standard deviation of your sample. Sigma is the standard deviation of your population. Okay. Since n is in square root, if you want to make your estimate 2 times more precise, you need 4 times more data. यहाँ पे दिख रहा है? N is in under root. So if you want to make your estimate twice as precise as the current one, तो तुम्हें 4 times more data चाहिए. You need N to be 4 times more. The sample size या तो तुम्हारी जो overall population है, वो 4 गुना ज्यादा होनी चाहिए for your estimate to be 2 times precise. Which is standard error को by 2 करना है तो. So standard error measures the spread of average. How precise is your estimate? And precision is expensive. You need 4 times. अगर तुम्हें 4 गुना better करनी है अपनी precision, तो तुम्हें 16 गुना ज्यादा data चाहिए. This is how expensive precision is in stats. So for this, I think we'll stop here in this video. We've covered the zoo of distributions and what if your data is clumsy, how the normal maths कैसे लगानी है, central limit theorem is the magic, and your standard error or standard deviation के बीच का फर्क. In the next one, we'll cover estimation and confidence intervals and आपकी hypothesis testing. These are the two concepts we're going to cover in the next video. Thank you so much for watching, guys. I hope this was fruitful. Do like and share the video if you like the content, and feel free to ask any sort of doubts in the comments. The link to the drive where you can find our interview Bibles, not only for stats, but for almost anything that you need, is there in the description and the first comment. And the link to our WhatsApp group is also there in the description and the first comment. So do check out Prep Noob Society on WhatsApp as well. And do subscribe to our channel for more such amazing content. Thank you so much. And see you in the next video. Take care till then. Bye-bye.